on chapter 3 on probability. So probability theory is a well-defined branch of mathematics. Kolmogorov described a set of axioms in 1933 that are still in use today as the foundation of probability theory. We will implicitly use these axioms in our analysis. The interpretation of probability is a somewhat contentious matter. Some people believe probability quantifies the frequency of the occurrence of some event that is repeated in a large number of trials. Others believe it quantifies the state of our knowledge or belief that some event will occur. I will say that the things that you'll hear, that the terms are frequentist, the frequentist position on probability theory, and the other one is called Bayesian understanding, which has to do with your a priori knowledge of the situation, or the a priori probability that something will happen, and that has been a little bit contentious. However, Bayesian inference has become very much accepted. In the last 30 years, it's become the standard, maybe 40 years. It's become understood to be superior in some realms in terms of inference. So, but still, what exactly probability means, sort of philosophically, is a little bit contentious. In experiments, our measurements are tightly coupled to probability. This is apparent in the questions we ask. Here are some examples. How common is a given event? What is the probability we will reject a good theory based on experimental results? How repeatable are the results? How confident are we in the results? What is the character of the fluctuations and drift in the data? How much data do we need? These sorts of questions have probability theory sort of underlying them, and trying to answer them is something that we'll need probability theory to answer. It's very tightly tied for us to measurement, but also some theory of the physical phenomena include probabilistic models. Most paradigmatically, of course, is quantum mechanics in that regard, where positions of things are described by probability distributions and not by deterministic locations before the measurement takes place. So, that's the probabilistic aspect of the physics. Then there are also many other probabilistic aspects of the world. In measurement, it's probably the most significant aspect. So when you're doing things like feedback control, you're always going to be measuring something, and having a model of the noise in that is important. Anytime you're estimating a parameter from experimental data, probability and the probability distribution of your random variable that you're measuring is very important. And so probability is very important for us, which is why, even though I know that you guys all have seen it to some extent, I'm going to go fairly far into probability and statistics, because I think it's worth reviewing, even if you've seen it. Do you have a question?
Question here. If I see the question like 1 to 6 here,
Yeah.
I thought it asked the statistics.
They're related.
Yeah.
So statistics is, you can think of it as being like applied probability. We'll when I get to the statistics chapter, I'll try to sort of explain how statistics is different. It is different. It can be kind of considered to be more of an applied situation. Typically, the way that it's explained is that probability is concerned with distributions and random variables, whereas statistics is concerned with samples, like data, like finite number of samples and data. And some of these questions are are quite more in the realm of statistics than in probability.
Confident interval.
Yeah. How confident are we in the results? But all of those ideas of like confidence and stuff, they're all built on probabilistic models of probability distributions, like Gaussian distribution for white noise and all that. So it's really a mischaracterization of statistics considered to be separate from probability theory. It's really more like a subfield of probability theory, or an applied aspect of probability theory.
In the end, we will use the data to predict something will happen, so it will come back to probability.
Yeah, for us, probability theory pretty much always turns into statistics, because usually we're interested in measuring something, and then we're going to have a sample of the phenomenon, and then we gotta infer things from that. So yeah. Okay, any questions on this other than that? All right, see you guys next time.